Okay, so this PowerPoint is really going to hopefully quickly talk you through the basics of irrational numbers for junior cert higher level. I'm going to get started pretty quickly here. First thing to be covered is natural numbers. So a natural number is positive, and it's a whole number. Positive and whole number, and it's denoted by a capital N. Integers have not made it onto this slide for whatever reason. It's being cut off, so they're positive or negative whole numbers. So any negative number, any positive number, as long as they're whole numbers. And again, this goes on forever, forwards and backwards. The only difference between natural numbers and integers is integers include 0 and all of the negative numbers here as well. And then the final one that would have been covered in first year is rational numbers, and they're denoted by capital Q. So a rational number is A over B. Basically, it can be a fraction where A and B are both integers. They're both whole numbers. Elements of Z is a fancy way of saying that. So A and B are both elements of the integers. So the thing about this is that, for example, it can include something like 3 over 2, which is 1.5. So it fills in all the gaps in between 1, 2, 3, 4, 5, 6, in between all the whole numbers. The rational numbers fill all that up as well. Now it does also include something like, for example, 4 over 2, something that can be written as a fraction, but if we simplify that, it's just the number 2. So all the integers and all the natural numbers also form part of the rational numbers. The number, for example, minus 4, we could just write that as minus 4 over 1. It's still got the same value, but now it's written as a fraction, so we know that minus 4 is a rational number as well. Just the properties of operations here. This isn't hugely important, but just as a recap, commutative means you can rearrange the order, so A plus B is equal to B plus A. 2 plus 3 will give you 5, or 3 plus 2 will give you 5. Doesn't matter what the order is, you can mix them around. So that's true for addition, and it's true for multiplication. 2 times 4 is 8. Similarly, 4 times 2 will give you 8. So it doesn't matter which way we do it. We also say that addition and multiplication are associative. So if we have A plus B plus C, we can group the A and B together and do A and B first. Or we can group the B and C together and do that first. But addition, it doesn't really matter what order we do it. And it simply doesn't matter how we group it. Same thing for multiplication. And then the final thing is just multiplication distributing over addition. Again, this is stuff that was done in first year. Honestly, doesn't really come up in the course much. So if we have 3 times 4 plus 2, we can split that up and say it's equal to 3 times 4 plus 3 times 2. So we can say that's equal to 3 times 4 plus 3 times 2. So commuting is moving to and from work, so we can move them around. Associative, an association is a group, so it doesn't matter which way you group them for addition and multiplication. And distribute means to give out. So we give out 3 to 4 and we give out 3 to 2. 3 times 4 and 3 times 2. BIM, this is something you would have been familiar with last year. It's basically just the order of operations. So if we're given a question to do, we do the brackets first. Then we do the indices. Then we do multiplication and division going from left to right. And then we do addition and subtraction going from left to right. Again, that's more of a recap, not really the focus of the video. There's a few practice questions there if you want to have a go at them. So now we get on to these things called irrational numbers. If you remember, our final number system that we did in first year was Q, our rational numbers. And remember, they can be expressed as a fraction, basically, where the top and bottom are elements of the integers. So they're whole numbers on top and bottom. So an irrational number is any number that cannot be expressed as a fraction. Basically, for the junior cert purposes, this is going to fall into 2 categories. It's either going to be pi, which, if we work it out, is 3.14 something, or else a surd. And a surd is basically just a square root of a number that doesn't simplify to give you something nice. So square root of 2, for example, gives you 1.41421335 dot dot dot, and it goes on forever. And same thing, pi will go on forever. So 3.141592654, and it just goes on and on and on forever. So essentially the way I think of an irrational number in my head, it's a decimal that never repeats itself and goes on forever. So for example, if we had, 1/3, which we know is a rational number, because it's able to be expressed as an integer over an integer. But if we looked at that, that's the decimal that goes on forever. You might think, well, wouldn't that be an irrational number? It wouldn't, because it repeats itself, whereas any irrational number would not repeat itself. So basically any square root that doesn't work out, square root of 5, it's going to give you a irrational number, a decimal that never repeats itself. Square root of 7 will give you an irrational number that never repeats itself. Square root of 16 will be an example of one that doesn't, because that actually simplifies to a rational number. Memes, here's just enjoy them if you want. So yeah, an irrational number cannot be written as a fraction, where the top and bottom are both integers. So surds are irrational numbers, which can be expressed as the root of a rational number, is I think what this slide is supposed to say. I don't know why it keeps cutting off text on this video making software. So the examples there are square root of 2, square root of 3 will be another one. Square root of 4 is not a surd, because the square root of 4 is not an irrational number, it simplifies to 2. Square root of 5 is, square root of 6 is, square root of 7 is, and so on. Square root of 9 is another example of something that wouldn't be, because that just simplifies down to 3. So again, a surd is just an irrational number that can be expressed as the square root of a rational number. So square root of 2, because 2 is rational, 5 is rational, 7 is rational, and so on. So this is a little exercise we did, just looking at examples of how it all works, right? So if we look at the number 3, for example, 3 would be a natural number, so it would be inside an n here on a Venn diagram. But because it's a natural number, it would also be an integer, positive or negative whole numbers, so it's also inside z. It can be expressed as 3/1, so it's a rational number. And real numbers are basically going to be all of the numbers that we deal with for the junior cert. There is such a thing as imaginary numbers, but that's something you look at in 5th and 6th year, probably 6th year. So 3 fits in all these, right? An example of something that would fit in, integers would be -4, because that's a whole number, but it's not a positive whole number, so it can't go in natural numbers. So it's out here in the integers. We can express it as -4/1, so it's also a rational number, and it's also a real number, because every number you're going to come across is a real number. Something that's a rational number then would be, 5/6, because that can be expressed as a fraction. So that will go out here in our Venn diagram, because it's not a whole number, it's not a positive whole number, but it is a rational number. And it also is a real number. Again, you're not going to see any imaginary numbers on your junior cert course. And then finally we come out to the irrationals, so that would be where, pi would hang out. That's one of our classic irrational numbers, or any surd, a square root that cannot be simplified to give us a rational number. So now square root of 2, square root of 5, square root of 3, and so on. All right, so now we come on to the surd laws. Skipped ahead a few slides there. So yeah, kind of like indices, surds have their own set of rules that they need to abide by. So this first surd law here, square root of a times by the square root of b. What we can do to simplify that is just get the square root of both of those multiplied together. So a practical example of this will be square root of square root of 8 times by the square root of 2. Well, we can just simplify that by multiplying the two square roots. So that's square root of 8 by 2, or we could say it's the square root of 16. And that simplifies 8 to 4. So that's a nice example of third law 1. For third law 2, if we have two square roots divided by each other, then we can just get the square root of the numbers divided by each other. So square root of a divided by square root of b is equal to the square root of a over b. An example of this, we could say that square root of 50 divided by the square root of 2. If we're asked to simplify that, well, we could try using third law 2. So we could put in square root of 50 over 2. 50 over 2 actually conveniently gives us 25. Keeping that square root still. So the square root of 25 in this case would just give us 5. So there's an example of third law 2. Third law 3 you maybe intuitively know yourself. So a square root times by a square root will cancel out. You know, if you think about this yourself, right? 3 squared, for example, gives us 9, but then the square root of 9 brings us back to 3. So multiplying a square root by itself cancels it out. Squaring a square root or getting the square root of a square number cancels it out. So just an example of this then would be, you know, square root of 5 times by the square root of 5. Square roots cancel each other out. You're just left with 5. Or a more common way for you to see it would be the square root of 5 squared, which literally means multiply the square root of 5 by itself. So it'll be root 5 times root 5, which just gives us 5. And that's not particularly complicated. You might feel like you're missing something there, but that's all it is. So look, there's a few examples tried with some answers for third law 1 and 2. This is kind of working backwards here with third law 1, so this can be kind of useful sometimes. If you want to simplify a third, like for example, I'll do e square root of 75. The way we can do that is try and split up 75 into its factor pairs. So 75's factor pairs, I might do that as rough work over here. We can split 75 up into 1 times 75. 2 doesn't go into it. 75 does divide by 3, I'd say. So 3 times 25. 5 goes into it. 5 times 15. Right, so I think they're all the factor pairs. So what we're doing here then really is just splitting it up. We're trying to find a nice square number basically. And 25 is a square number, so we're going to use these two. So we're going to split up our root 75 using third law 1. It's root 25 times by root 3. And again, third law 1 says that this multiplied by this will be the square root of the two numbers multiplied. So 25 times 3 gives us 75. We're just working the opposite way with this. Now the reason why I chose a square number 25 is because that easily simplifies to 5. So we can simplify this to being 5 times the square root of 3. So that's a way of simplifying third. Let's go for an easier one just to get another one done real quick. Square root of 8, we can try to simplify that. So we get the factors of 8. 1 times 8 or 2 times 4. The square number here will be 4. We're looking for the biggest square number if we can get it. I'm going to rewrite that as root 4 times by root 2, because 4 times 2 gives us 8. And I'm put the square number in front, because the square root of 4 is 2. So square root of 4 simplifies to 2, and root 2 just stays as root 2. So we can rewrite 8 as just a simpler form. So here's a more complicated question that uses this principle. So this time we've been given root 50 plus root 8 minus root 32, and they're asking us to simplify those thirds. So we're going to simplify each of these individually, and then we're going to see that we can go somewhere from there afterwards. So square root of 50, we can split up into root 25 times root 2. If we list out all factor pairs, 25 is the biggest square number that's a factor. Square root of 8, we can split up into square root of 4 times square root of 2, like we did in the last slide, because square root of 4 is a square number. And square root of 32, we can split that up into root 16 times root 2, because 16 times 2 gives us 32. And 16 is the biggest square number that shows up as a factor of 32. So 25 times root 2, the root 25 simplifies to 5. For the next one, root 4 times root 2, root 4 simplifies to 2. The last one, root 16 times root 2, the root 16 simplifies to 4. She gives us this next line here, 5 times root 2 plus 2 root 2 minus 4 times root 2. So if we have 5 of something and add 2 of it, we're going to end up with 7 root 2. And if we have 7 root 2's and we take away 4 root 2's, we're going to end up with 3 root 2's. So this is very similar to, if we have 5x and we add 2x and we take away 4x. 5x plus 2x will give us 7x. So have to take away 4x. So 7x take away 4x will give us 3x. Very same thing, it's just that instead of x's here we have root 2's. And we're fine to add all those with each other because our surd here is the same. It's root 2, root 2, root 2. So completely fine to do that. A couple of questions you can practice. Another little type of question here that actually kind of brings in an index law, to be honest, instead of a surd law. But right, if we have two numbers and they're multiplied by each other and we have to square the whole thing, what we can do is square the first number and square the second number separately. This doesn't work if they were added to each other or subtracted from each other, but it does work if they're multiplied by each other. So we have a times by square root of b. So we can break that up and say it's a squared times square root of b squared. So a squared will just stay as a squared, and a square root squared in this case, the square root and the square will cancel each other out. So we're just going to be left with b. So a squared b will be our answer here. Okay, so now we get on to multiplying surds. The way we do this, I'll just do the first one here. So we have root 2 times 1 plus the square root of 5. Just multiply the outside term by the two inside terms. So root 2 times 1, anything that times by 1 just stays the same. And root 2 times root 5, we can use our surd law 1 to figure out that's going to be the square root of 2 times 5, so the square root of 10. Okay, if we look at the second question here, we have 2 plus square root of 5 times by 3 plus the square root of 5. So what we're going to do this time is split that first bracket up into 2. So we're going to have 2 plus the square root of 5. And then rewrite the second bracket out twice. 3 plus the square root of 5 is our second bracket. 3 plus the square root of 5 is our second bracket here. And now we do the same thing as we did before. Outside number times by the two inside numbers. Outside number times by the two inside numbers. So 2 times 3 here is going to give us 6. 2 by root 5 is just going to give us 2 root 5, which means 2 by root 5, or 2 root 5s. Root 5 by 3 is going to give us 3 root 5, 3 by root 5, 3 by root 5. And our root 5 times by root 5, surd law 3 says it simplifies to just give us 5. So we can simplify our answer here actually because we've got normal numbers and we've got root 5s. So let's bring our normal numbers next to each other. 6 plus the square root of 5. Normal numbers, underlined in red above, I'll underline them in red here. And then we've got 2 root 5 plus 3 root 5. underlined in green above, underlined in green here. So 6 plus 5 is going to give us 11 here, right? So our normal number simplified to 11. And 2 root 5 plus 3 root 5, if we have 2 of something and we add 3 of it, 2 plus 3 is 5. So we're going to end up with 5 root 5s. Just like if we had 2x plus 3x, we'd have 5x. It's the same thing as that, if the surd is the same. So this will be our answer for that one. There's one other type of question here that maybe is kind of tricky. Just this last one here, 3 plus root 6 squared. I'll have a look at how to start that question with you. And I don't think I'm going to do it out because I'm running out of time and I have to go teach a class soon. Okay, so if we had to square this, what we'd be doing is we'd multiply it by itself. So 3 plus the square root of 6, multiply by itself, 3 plus the square root of 6. So we would split this first bracket up and rewrite the second bracket out twice. Just make sure we keep that sign there as well for the plus root 6. Okay. And then look, same way as before, you just multiply this by this, this by this, this by this, and this by this. Outside term by the two inside terms. And if you do that correctly, you get a nice answer out. Using the same process as before, just simplify it at the end. The denominator. Okay, so now we come on to irrational. This is actually fairly easy to do. It sounds horrible. So, you know, in this question here, the denominator is a surd, so it's an irrational number. We want to rationalize it. So we're going to multiply the bottom by 2. And when we do that, we multiply the top by 2. It's okay to multiply the bottom or top by anything. You know, if I have a half, I can multiply the top by any random number, say 4, as long as I multiply the top by 4 as well. So 1 times 4 on the top here will give me 4, 2 times 4 will give me 8, right? 4 eighths is the same as a half. So it's fine for me to do this, as long as what I do to the bottom, I do to the top. So now, surd law 3 says that at the bottom here, root 2 times root 2 is just going to give me 2. So I have rationalized the denominator. The denominator is the bottom. Now it's a rational number. And root 2 times 1 on the top is going to be root 2. It might seem like this looks more complicated than this one, but it's actually a lot easier to work with fractions when your bottom is a rational number. Same thing over here. So we have this fraction, we want to rationalize the denominator. So we rewrite it, multiply the bottom by itself, multiply the top by that surd from the bottom as well. So here, root 5 by root 5 is just going to give us 5. That was our plan. So now we've got a rational number as the denominator. On the top, we're going to keep the 6. And then we're going to use surd law 1. So if you multiply root 3 by root 5, we get the square root of 3 by 5. Or we can say that we get 6 times the square root of 15 on top, divided by 5 on the bottom.